I'm going to give you guys a little kind of peek behind the scenes of what it's taken to scale YouTube. Since this is only a half-an-hour talk, I can't really go into a whole lot of detail, but this should give you some idea of what it takes to provide one of the largest sites in the world. Okay, so the general kind of layout here is that I'm going to talk about a little historical context, set things up, talk about a few pieces of our scalability, some of the key challenges we've faced, lessons we've learned, and go into Q&A. So this graph, this shape of graph appears very often. I guess in the context of this presentation, it can mean a number of things. Well, it could probably correspond to the price of a gallon of gas, but I'm not going to talk about that. Google has great food, so I think that was true, but I'm not going to talk about it either. I'm still scarred by that. But the thing that it does actually represent is the daily video views over over our lifespan. So it's pretty amazing the growth that we've had, and it's kind of interesting when you see like at certain points when we've added machines or whatnot, we added capacity, made things faster, added some great features, then the graph definitely spikes up a little bit. Okay, so quick timeline of YouTube. February 2005, we were founded. We received our first round of VC funding in October 2005, so 8 months later. So we got our first office. And one of the more interesting scalability challenges we had, or one of the more interesting engineering challenges we had, was trying to keep our monitors dry in our new office. So the first day that we moved in, it started raining, and which is normally fine when you're in a building, except that there were about, I don't know, 7 or 8 different leaks in various places. And we had just gotten our new nice, big 24-inch monitors, and we didn't really want them to have any kind of issues with the water. So we, after maybe like 20 or 30 minutes of trying various things, we took the plastic wrapping from our IKEA furniture, we fashioned a funnel out of that, and we used the rubber trash can to catch the water. We had just enough trash cans and just enough plastic that we were able to divert large pools of water into the trash cans. And I think I drove back once just to make sure that the trash cans weren't like overfull. So definitely interesting times already during that time. Just about 5 months later, we actually hit 30 million video playbacks per day. That was only 1 year after we were founded. So pretty amazing numbers. And I'll go into a little bit of details to what it took to get there. A few months later, we more than tripled that number. So pretty amazing. It was kind of interesting. We'd add like 5%, 5% or 10% capacity, and we'd get as much, if not more, traffic gained from that. So it's kind of interesting. A few months later, we got acquired by Google, and my personal favorite part is we got a lot of free food. So that made me quite happy. And the crazy thing is that by the time we were acquired, we were already a top 10 site by various external measures, just top 10 period across all websites. So pretty amazing, only considering that we were only maybe about a year and a half old at that time. We were number 4 in Alexa by Q3 2007 and by other measures as well. And today, I think there's a new updated number now, but last I heard there was 10 hours of video uploaded per minute. It might be more like 13 now. And hundreds of millions of video playbacks per day. It's certainly a lot of playbacks per day. I can't give the exact number, but it's pretty mind-boggling. So real quickly, the pre-acquisition team, we had 2 sysadmins, 2 software guys, like myself included, making sure that the site scaled, 2 feature developers, 2 network engineers, 1 DBA, and unfortunately no chefs. And now we have 2 as well, so I guess the theme of 2 continues. Here's my little algorithm for handling rapid growth. You start by identifying and fixing bottlenecks. You drink the beverage of your choice. I'm not suggesting anything. You just drink the beverage of your choice. You sleep a little bit, and you notice something new, and you start all over again. That's how it is, I guess, with a rapidly growing site. One of the key phrases that we had in the early days was, "These are good problems to have," and after a while, we're like, "I'm going to kill the next person who says that phrase." Well, that's a good segue into my next slide. because yeah, in this particular case, there's a little bit of drinking and sleeping going on there. This is one of our 2 sets of minutes before the acquisition. All right, so to move into some of the nuts and bolts here, we have a web request flow. Starts with an end user, then the request flows from the user's browser to a set of NetScaler load balancers. From that goes to the web servers, and this is a bank of web servers in a YouTube colo. And these machines are, don't really maintain any local state. They're just like, one goes down, nothing really happens to the site. Within these machines, Apache receives the requests from the NetScalers. Checks to see if it's a dynamic request. If it's a dynamic request, it will forward the request on through FastCGI to a local app server, the multi-process app server running on the same machine, which is written in Python, our programming language of choice for all the application code here. And Python retrieves information from various places. It retrieves information from the RPC, from our memcache servers, which store information retrieved from databases and other expensive, relatively expensive data sources, and obviously our databases for things that either are uncacheable or are not in our caches. For video, we have 2 different places where video can come from. The first is our CDN. It's an internal project written by a group at Google, and that CDN takes care of a number of things. It basically takes care of the content that is most popular on the YouTube website. So the sort of the mega hits and the things that are maybe not be necessarily a hit within the U.S., but a hit maybe in Europe. Let's say, like for example, maybe some pretty interesting soccer videos, for example, which may be more popular in Europe. It takes care of serving of all those videos and makes sure that there are multiple copies of the video for quality of service, reliability, and also ensures that a copy of the video is relatively close to the user, so they're not going over various network hops, like too many network hops and a transatlantic link to get to the video. And for the rest of our videos, they're hosted on at YouTube colos in various places in the U.S. At least for right now. We're considering other locations, but for now it's the U.S. Key technologies. We use Linux, specifically the SUSE distribution of Linux, various versions of in the 10.x line. We use Apache, as I mentioned just recently, for serving of content through the youtube.com site, as well as, I think, the mobile site and some other things, and the API. And for video serving, we use Lite because it's just so much faster in handling large files. It just blows Apache away in terms of performance when dealing with large numbers of connections, a high connect rate, and large numbers of videos. Or, I mean, large file size, rather. MySQL is used for all the metadata storage, so things like user information, like users, the username, hash version of the password, etc., that kind of thing. And finally, as I mentioned, Python, and it turns out that Python was actually a very good choice of programming languages for us because, especially in the early days when it was very difficult for us to recruit people, especially when we were tiny. For a while we didn't have a full-time recruiter. It was just far easier to put out a purchase order to get 10 machines versus getting 1 or 2 talented engineers to magically materialize and start and get ramped up in our system. So we traded off sort of time to market and developer efficiency for for some other stuff, maybe slightly slower code, but code that's less susceptible to Stack Overflows and other nasty things that you might see in other programming languages. And finally, Google technologies. We use a number of things that you might have read about and seen. Obviously, search is one of the key ones. But aside from search, we use Bigtable internally for storing video thumbnails. We use GFS for a number of internal file storage needs. We use proto-buffers, which were recently open sourced, and just a number of Google technologies in general. And we're kind of scaling that out over time as we find specific problems that require massive computing power and require the distributed computing that the Google infrastructure affords us. For our databases, we started with one, and obviously, like any site, we started with one main one and a replica for backup and a replica for reporting. But we quickly outgrew that. We now have multiple vertical partitions, which are basically where when we take a part of the website that kind of stands on its own, and that part of the website doesn't have too many external dependencies. We took that, we stuck that part on a separate set of database machines and maybe even a separate set of web machines, and we said, okay, this can scale on its own. It doesn't have to bother like the rest of the site. And same thing with other parts. For parts of the site that were sufficiently large and that were hard to disentangle, like for example the user metadata and the associated video metadata, we did horizontal partitioning where we split it up. Like we have multiple database instances with the same schema, but different sets of users. So one nth of our users are in this partition, one nth are here, one nth are here. And we did that just because that seemed to be the most scalable way to do it. And then we have a lookup database that allows us to associate a user with one of these partitions, so that common operations like watching a video and seeing a user's channel page are much quicker than they would be otherwise if we had to scan through each of the databases. Those scalability challenges, we've had a number of major challenges. It seems like every time we add capacity, there's a number of things that can sap away the capacity. The first was rapid and unpredictable growth. It's pretty amazing, like as I mentioned before, when when it seems like no matter how much capacity you add, the users come back and consume all of it. It's gratifying and it's rewarding, but at the same time, it's definitely a challenge because, especially in the early days, we didn't have the budget, pre-acquisition and even post-acquisition. There's still only so much you can do when you build in a certain kind of buffer and then the growth just eats through all that buffer and more. So it's an interesting game to play. Not having too many excess machines around, not spending too much money at one time versus trying to keep up with user growth. Passionate users, we couldn't have foreseen when we started this site that some users would have thousands and thousands and thousands of videos, and people would want to do video blogging like for every second of their life, things like that, and those are good uses of our site. But it just means that we need to work a little bit harder in some of these cases to make sure that we can accommodate these types of uses. New features. A couple years ago, the video space was kind of brand new, and you were lucky to be able to play a video without installing some kind of OS-specific plugin or whatever. But now there's definitely a higher baseline, right? I mean, not only do you need to have ubiquitous access to videos, embeddability, APIs, all that stuff. All that stuff is assumed. Now you get into stuff like recommendation algorithms and social graphs and all sorts of things that are not computationally cheap. So it's certainly a challenge to try to balance user experience, new features, and scalability of the site. Pushing hardware and software boundaries. I'll talk a little bit about this later on. But basically, when you run hardware and software too close to its limits, it's more likely to fail. And I'll go into a couple of examples of of times we've run into these kinds of issues. And finally, performance bottlenecks are getting very obscure. I mean, we file bugs with we file bugs with a couple of the vendors that provide support for our open source software, because sometimes we want a little extra few people to help look at some issues. And it turns out that when we forward those bugs to them, they're like, really? And then they spend a few days reproducing it, and then they don't really have any kind of real solution for us. It's kind of interesting when you get to that level, and when you start Googling for stuff, and when you start searching blogs, and you don't find anything like about the problem that you're encountering. It definitely puts you in an interesting spot. And some of these problems can be solved by having more headroom, but for software and for some of the software stuff, we're pushing it in ways that I don't think the creators ever intended. So here's one example of an issue we had. You can, if you can't read it, it says, we can't accept any more videos, too many videos. So this was sent at 2:24 a.m. on October 22nd. I was about to go to sleep at that point, and this wasn't a very pleasant email to get. And basically, our video uploads had ground to a halt. And after a little bit of debugging, it didn't take very long, we figured out that, well, you know, we sort of did the original boneheaded, but let's get it out kind of, like startup kind of mentality of putting like, storing the video thumbnails for each of our videos into like separate subdirectories, but all those subdirectories were in one like flat directory structure. So we had tens of thousands of files in one directory. Not a good idea. So, you know, we ran into an inodes per directory limit, at least on ext3, which was the file system we were using. Pretty bad thing, and you know, it's not something like, it's obviously not rocket science that you shouldn't put too many files in a flat directory structure, but you know, we were trying to keep up with growth, and it wasn't too hard to solve it, right? I mean, we went to like a tree structure, a hierarchical structure. It just wasn't the most pleasant thing to code at that time of night, that's all. And to test, and under the pressure of, you know, all the video uploads failing in the meantime. So it wasn't the funnest thing. Another thing was, going back to the earlier comment I made about pushing things to the limits. We were pushing our database to its limits because we hadn't developed the infrastructure required to partition it yet. It's a difficult problem. So this email, or this posting, I should say, this article from CNET was covering our downtime that we had. It started at 7:30 a.m. and went for 5 hours. It was very unpleasant. I think even more unpleasant than the actual downtime was the fact that my parents were calling me, asking me if I was okay, and you know, asking and trying to lend me their moral support. So I was like, I just need to deal with this, you know. So and we were, you know, we looked at the logs, and MySQL had given us an error. The error was that checksum had failed. And the reason, and what happens when MySQL reads data from the disk is that there is a checksum stored for every page, which is about 16K, I think. It's stored on disk, and then when MySQL reads the data from the disk, it calculates a new checksum and compares that against what's stored on disk to make sure that nothing in between the disk and the process is messed up, and the data is actually intact. Turns out that they didn't match, so MySQL kills itself at that point. And not only does it kill itself, it takes 4 or 5 hours, or depending on the volume of transactions and what the volume of changes that have not been flushed to disk, it will take, you know, 4 or 5 hours to recover. And at that point, a lot of us, we didn't have a dedicated DBA at that point, or he had just joined, he didn't know MySQL yet, and I was filling in for that. Anyway, we went through all sorts of stuff to try to figure out what the culprit was. We searched everyone online. We found a lot of questions, but no answers, like no solutions to this issue. And we frantically put a whole bunch of orders out for different pieces of hardware that may not exhibit the same issues. We were thinking maybe it's a hardware issue because not everyone is having this, and lots of people use MySQL, and some of these people are bigger than us. And after a long period of time, we happened upon one blog post, exactly one blog post written that very day, saying that there is an issue with this little guy, which is sticking out with the expansion slot. It's a riser card, because we had recently, for performance purposes, switched from a 4U machine, which is taller, to a 3U machine, because the 3U machine could be outfitted with a faster I/O subsystem, at least for the vendor we were using. And the shorter shorter height meant that we couldn't accommodate a full height expansion card like the RAID controller that we had. So we had to put a riser card so that instead of going like this, the card goes like this, where there's plenty of room. And it turns out that the combination of the RAID card and the riser card would sometimes cause interesting fluctuations in voltages that might cause an inverted bit every now and then. So that's exactly what happened. The data was fine on the disk. We validated it after it crashed. It was fine. But somewhere in reading the bits off the disk, something went wrong. But you know, that was definitely a very tense 2 or 3 days, or weeks rather. And the next thing I'm going to mention is actually one of my favorite ones. So we were again going to run out of disk space because we were having, you know, vendor issues, trying to get things in on time, and growth was just explosive. So we did the right thing, which is to order machines like slightly early, and we said, oh, let's rush a shipment to us. Problem is that the shipment was rushed in the wrong way. It ended up. Actually, I don't even think like this is where it originally was. I think it ended up on someone's BMW originally. It was unloaded unceremoniously in someone's car. So that was an interesting thing. We scrambled, we worked around this, but it was not pleasant when you have 40 machines costing a couple of $1,000s a piece, and your lifeline for accepting more videos on the concrete probably broken. So okay, so I'm gonna wrap up here. So basically, things that we did to scale is we kept our code very simple. We made sure that all the pieces were very simple so that we can optimize, so that we can debug issues, so that we can refactor. We iterated on pretty much everything that we possibly could have. Software like database, caching, etc. You know, we tweaked the patches configuration file a number of times. We tweaked OS buffers. We even tweaked our RAID settings, and we use a hybrid of like software and hardware RAID for our databases. We tweaked the amount of memory in our system. So pretty much everything. It was a very iterative process. The last thing that worked in our favor is I think we had just a really good team. I'm pretty honored to be a part of this team. Had a lot of fun. You know, this was kind of a nice experience where we were celebrating reaching 100 million video views per day, and we decided to grab some burgers, and this particular restaurant serves champagne with their burgers, so it's a lot of fun. All right, so I have a few more minutes left. So any questions that you guys have? Excuse me?
You send any thank you thing for that guy suggest a solution to solve the big problem?
Yeah, and we also hired him for a little bit too, so that's fine.
How long did it take him to find out what the riser problem?
I think he was actually, like, we didn't hire him for that particular issue. It turns out that he was helping another customer, and he had posted about the experiences that he had with the other customer. So we forgot to ask him how long it took to figure out that issue. But yeah, it definitely took a while for us to settle on that, because we had to swap out all the RAID cards on all of our machines, which is not very fun when the databases are actually running. Yes?
Can you speak a bit about your content conversion engines, how you accept content uploaded and convert it to the format you're going to serve it in?
Okay, so we accept, I mean, this is somewhat in flux right now, but the way that we've been doing it since we were pretty much founded is that we accept the content through an HTTP post, from the web browser, or from the API or whatever, and then from that we perform a couple of steps. We do sort of identification to make sure it's like actually a video, for one thing, because some people upload like PowerPoint files and stuff like that, and we don't support that. And frame rate detection, source detection, etc. We do a number of things like that, and then we after that we put it through transcoding with using the settings that we detect, and then after that we take the transcoded file, we copy that to the machines that it's going to be served from. And for a couple of the other formats, there's like H.264, there's a couple other formats like for the mobile phone, etc. Those happen currently after the initial FLV encoding, as well as the higher quality version. So that's at a high level, at least, what happens. Yes? Mm-hmm. Excuse me, I didn't hear the question. Yeah. Let's see here. This one? Okay. Yeah, it's a little bit small, but I think I spoke to most of it, hopefully. Yes?
Are you sharding the database at all? Are you splitting? I imagine that you have ridiculously huge tables for some of the, like the users. You have 100 million companies serving your stuff, so they're running across. You have to partition the databases in some pretty ridiculous ways.
Definitely, definitely. I spoke a little bit about that in a previous slide, where we do a combination of vertical partitioning for things where the table is manageable, the size is manageable, and maybe the traffic is quite high. But for things where both the size and the traffic are particularly challenging to cope with, we do a horizontal partitioning, where we have a set of master databases with different sets of data in each of them, and each of those have replicas so that we can issue reads to those in an efficient way. So that's how we handle it. And then we have a lookup database to map users and videos to each of those partitions. Does that answer your question? Or?
It does kind of. I spoke with some people from I5, and they were saying that they actually broke it up even beyond that, where each table was actually broken up further into different shards.
Mm-hmm.
And they were using, they weren't using MySQL because MySQL's indexing was there was too much overhead for each one of those. So I was surprised that you were using MySQL, but
Mm-hmm.
so I was curious how you're dealing with some of those issues.
I think our usual solution for a lot of this is to partition more. I think that helps a lot, because we found that database has a sweet spot, which is, it's kind of hard to figure out what that sweet spot is, except through empirical, actually trying things out. 'Cause it turns out that not all the data has to fit in memory, just the data that you need to use within a certain period of time, like the working set, in other words. So we found that the memory to disk ratio is probably the key thing to scale. And a number of the other, like the indexing and all the other stuff, we've tweaked that over time. One last question, yeah?
Did you guys build on some sort of a toolkit for that, to implement the scaling of it?
No, it's a lot of the stuff that we've done is kind of homegrown. I think we have a very light layer on top of the Python DB API thing, MySQL Python. And we just built kind of our initial layer, which is dealing with a single database. And then as time went on, what was kind of nice about Python and other languages like Python that are high level is that we used this thing called a decorator around all the functions that access a database. And all it is like an intermediary. It's a proxy to the function. And that gives you the state that you need to talk to the database. And since we have that layer of indirection, we're able to plug things in, and we used a little bit of Python magic to make things work seamlessly, so that 99% of our code didn't have to change, which is pretty nice. Okay, I think I'm running out of time for questions, unfortunately, but thanks for listening.